The title of the talk is Estimation of Altitude in Stereoscopic 3D versus 2D real-world scenes. Lesley Deas received her Bachelor of Science in Psychology from University of Stirling and Master of Science in Neuropsychology from University of Edinburgh. She's completed her PhD in psychology at the Center for Vision Research at York University in Toronto.
Okay, thank you for that introduction. And it's nice that I followed on from Mark there, because we'll be looking at estimation of altitude in a military context. This is work that we did in collaboration with DRDC, Defence Research and Development Canada. Okay, so as we move through and interact with our environment, we often need information about the absolute distance of objects. This is for tasks such as reaching and grasping, avoiding obstacles, and maneuvering vehicles. So to obtain this information, our binocular vision can provide information about both depth and distance. Stereopsis provides depth information by virtue of retinal disparity, and we could extract the absolute distance of objects by, for example, monitoring the convergence of the two eyes. However, monocular vision can also provide cues to both distance and depth. So considering this apparent redundancy, what is the advantage of binocular vision? Indeed, the necessity and utility of binocular vision for various tasks has been studied in many contexts. Here, we focus on aviation. So the potential advantage of binocular vision to aircrew has long been a focus of research, but there are differing conclusions. As we've just heard from Mark, stereopsis may be important for tasks such as formation flying and aerial refueling. But this might not be surprising given that these tasks involve the estimation of the relative location of objects in space, and stereopsis can provide that information. Other research has suggested binocular vision might not be necessary for some tasks. Case studies of small aircraft landing have compared binocular to monocular or eye-patched performance. Reports show that monocular landings are successful. However, this comes with several high-risk outcomes, such as steeper approaches and increased cognitive load. But it's difficult to know whether these outcomes are the result of the loss of stereoscopic vision or the reduced field of view caused by patching one eye. Indeed, one of the obstacles in consolidating this research is the wide range of test scenarios and methods used. So in this research, we focus on one task, a task that has a single perceptual judgment, altitude estimation. Altitude estimation is common to many flight crew tasks, and here we'll be looking at both low hover and high altitude. I'll be presenting two experiments with the common aim to determine the role of stereopsis to altitude estimation. We'll be using real-world still images, which allows precise control over both 2D and 3D cues. So in experiment one, we focus on a low hover rotary wing scenario. This is common for debarkation type tasks. In this scenario, the flight engineer typically estimates the distance to the ground by eye. They may use the landing gear or the skid as a relative reference point to help inform judgments. So this is a schematic of our apparatus. The apparatus was designed to simulate the position of a flight engineer looking out a helicopter door, down past the skid and to the ground. So with that, our observer was raised up and was looking down an angled TV. Our 55-inch 4K 3D TV was angled at 45 degrees on a custom-built mount. And as you'll see in a second, the simile was designed in a similar way, such that when mapped onto the TV, the observer was looking down at a flat ground plane. So we'll flip to the stimuli now, just to show you. You can pop your 3D glasses on now. So the stimuli were created in Autodesk Maya. They were rendered in 4K. So first of all, this is the grass terrain. So as you can see how this maps onto our apparatus, we have our skid at a fixed reference point. The skid was present in every trial, and that's our relative reference point. So the camera was directed 45 degrees in yaw, 45 degrees down. So when that maps onto the TV, the observer is looking down at a flat ground plane. So I'll just wait till everybody gets some glasses, gets the idea of what's going on. And as we're going through, if you cover one eye as well, that will give you the impression of the monocular trials as well. So we can go on to the next image. So this was the stones terrain. So we tested a range of altitudes from 5 feet down to 0, and texture, scale, size, and density all varied accordingly. So with this image, we're at 5 feet. And if we go to the next image, we're at 0 feet, or on the ground. Can you tell the difference? Maybe we could go back one. So this is 5 feet, and the next one is 0. Okay, so if we're on to the next image, this was a runway terrain. So here, the width and position of the yellow runway line was varied specifically so that it could not provide a monocular cue. And if we can go on to our next image, this is what we called the cross terrain. Now, this was the important control condition. Here, we are isolating the effect of disparity. This cross pattern was invariant at all altitudes, so the position of the cross never changed. So this is, again, altitude 5 feet, or highest altitude. And this is a pretty nice one where you cover one eye, you get the impression of the monocular view. So if you cover one eye, would you still say it's at 5 feet? Okay, so we can go back to the presentation. Thank you, Dan. So the observer's task was to estimate the altitude of the helicopter, or the distance to the ground. To do this, they first assigned a number that represented the distance between their head and the skid. They then used that number to then estimate the distance between the skid and the ground. So I'll try and break that down, explain that a little more. So the real distance between the head and the skid was about 6 feet. But when I ask the observer, what's the distance from your head to the skid, they may assign the number 10. That was a commonly used number. And then if I present the test image of 5 feet, an appropriate scaling would be then to assign the number 8. They're not suddenly going to be in the hundreds. So we compared 3D trials to 2D, or patched trials, and the terrains were interleaved. So here I'll present the results for experiment 1. On our x-axis, we have the altitude in inches from 0 to 60 inches. And on the y-axis, we have our normalized altitude estimate. The dashed line represents predicted accurate performance based on the geometry of the scene. So I'll first show the results for the monocular trials. So here you can see that performance is underestimated for all conditions, but I can break that down a little more. So for our terrains with monocular cues, the grass, the stones, and the runway, there is a significant increase in estimates as a function of altitude, but the slopes are very shallow. But we do see a systematic increase with more prominent cues, from the runway to the stones to the grass that gives the highest estimates. Now with our cross terrain, that's displayed there in red. Now recall that this condition did not provide any scalable monocular information. And here we see that the slope is not different from 0. It's simply as if the observers were stereotyping their responses. So now let's look at the 3D trials. And I'll first focus on the results for the cross condition. So here, only disparity information was available to inform altitude estimates. So where do estimates fall now? So here we see performance is much improved. Now we have now estimates increase in a monotonic fashion and are very close to predicted accuracy. So this suggests that stereopsis in isolation can be used to accurately estimate altitude. And then if we consider our terrains with monocular cues, here we see performance is enhanced and maps very well onto predicted accuracy. So this suggests that 2D monocular cues can help scale the depth from disparity. Indeed, the fanning out that was present in the monocular trials now converges onto the predicted accuracy. So with experiment 1, we showed that when estimating low altitudes relative to a fixed reference point, there is a clear benefit of stereopsis. Observers' 3D estimates were much improved compared to monocular alone. The observers' estimates were most accurate when both monocular and monocular cues were present, and this suggests that there's an important interplay in this range. But critically, estimates were accurate even in the absence of 2D texture information. suggesting that stereopsis in isolation provides a strong cue to altitude. So with experiment 2, we are going to higher altitudes. So altitude estimation may also be important in a rotary wing call to landing scenario. In this scenario, an aircrew member calls out altitude at regular intervals as the aircraft approaches touchdown. Callouts are visually based and begin at over 100 feet. So with experiment 2, we aim to determine if stereopsis provides a benefit to absolute altitude estimation at high altitudes. And again, we'll be using real-world scenes. Here we'll be using a desert, a road, and a snowy terrain. So in these scenes, monocular and binocular cues are present. The observer may be able to track the object size or the texture scale. And in the binocular view, the observer may be able to track their vergence angle. However, it is known that vergence is less effective at these distances, so we might predict that monocular cues may be dominant here. So we can go back to the stimuli, please. So I'll show you, we use both natural and simulated images here. And the first thing you'll notice is that there's no skid. This is an absolute judgment, and they're judging the distance directly from the eyes to the ground. So this was our natural scene, a snowy terrain. This was captured by my colleague Mackenzie Glayholt at CFB Borden in Ontario in February in the snow, hanging outside a helicopter. The things you do for science, eh? So this was we're looking almost straight down to the ground here at a viewing angle of 10 degrees. And this is our maximum altitude, 100 feet. And in the next image, we're down to 10 feet. So you can see the clear change in monocular cues here. So in our next scene, I went for the warmer option. These are simulated images captured in the Arma 2 game. So this is what we call the road terrain. So again, this is at 100 feet, looking down nearly 10 degrees. And our next image is, oh, sorry, I guess we don't have 10 feet there. We're onto the desert now. So this is the desert terrain. It's a much more sparse terrain, but there are still monocular cues present. Indeed, so this is at 100 feet, and our next image should be at 10 feet. So you can see the clear change in monocular scale here. Okay, so we can go back to the presentation. Thank you. So the experiment took place in a screening room with multiple viewers tested simultaneously. The images here were displayed on a large cinema screen, much like this one. And the observer's task was to estimate the distance to the ground. So to do this, observers performed a magnitude production task. They were first shown an image of altitude 40 feet and asked to assign a value that represents the distance to the ground. They then used that ratio, that modulus, to judge all other test altitudes. So again, I'll give you an example. So if they were shown the reference of 40 feet, they may assign that as the value 100. Again, I don't care about units, I just need that number. So then an ideal observer, when shown the test image of 10 feet, would assign the number 25. It's all proportions. So here I'll show the results for our 3 image sets. On the x-axis is our altitude, it's now in feet, and the y-axis is our normalized altitude estimate. And we'll be comparing 3D to 2D trials. So as you can see, in all image sets, there is an increase in altitude estimates with an increasing altitude. But our key comparison here is the 3D to the 2D. And in our snow and road terrains, there is no difference between 2D and 3D. But in our desert terrain, there is a significant difference between image sets. But we're reluctant to place too much emphasis on this result, given that, while significant, the effect size was very small. It was less than 1%. So for experiment 2, we show that stereopsis does not provide a consistent benefit to judgments of absolute altitude. In this scenario, monocular cues alone were able to support the appropriate scaling of altitude. So to summarize these experiments, we focused on 2 tasks. We looked at the relative and absolute altitude estimation in tests that are commonly performed by flight engineers. In experiment 1, we found that stereopsis provides accurate estimates in a low hover scenario with the presence of a fixed reference point. In contrast, in the absence of a reference point for an absolute judgment, Stereopsis provides no consistent benefit at high altitudes. But it might not be surprising that monocular cues dominate at high altitudes. Research in VR and in the real world has shown that vergence is less effective at distances beyond about 2 meters. And monocular cues are effective at indicating far distances. So our results show that monocular dominance extends to altitude estimation. But what happens when monocular cues are unreliable? Indeed, from an operational perspective, there are a number of documented accidents that may be caused by the misjudgments of altitude. For example, aircrew are trained to use tree height as a monocular cue. However, this cue can vary across flight situations. California is different from Ontario, is different from Scotland. So if there are errors in assumed tree height, the aircrew's altitude estimate will also be inaccurate. So our results highlight the importance of terrain-specific training. And given the dominance of monocular cues in this situation, the role of individual monocular cues is an area that requires further study. But where we did find an impact of stereopsis is at the relative low hover situation. Here, while both monocular and binocular cues separately influenced estimates, stereopsis alone is a cue to accurate altitude estimation. And again, this has important implications from an operational perspective. So stereopsis may be important when monocular cues are absent or unreliable. So in blowing snow or in a dust cloud, and this is common for debarkation, taxiing, terrain scouting, stereopsis may provide vital information for aircrew in these scenarios. And this is the focus of ongoing research with DRDC. So I'd just like to thank our collaborators at University of Waterloo and DRDC, and thank you.
Thank you.